Imagine, just for a second, that you invent a really smart robot vacuum.
Okay, I'm with you.
You spend years in your garage tinkering with its physical sensors,
Yeah.
right? Like coding its navigation algorithms, just trying to make it map the perimeter of your living room perfectly.
So it stops bumping into the couch every 5 minutes.
Exactly. So it stops hitting the couch. And then one day, you look at the raw code you wrote for this vacuum and you realize that somehow, entirely by accident, it perfectly explains the complex mechanics of human digestion.
Which makes absolutely zero intuitive sense.
Right. Down to the enzymes. It's wild. Why would a floor cleaning algorithm have anything to do with biology? But that is exactly the kind of mind-bending, almost impossible paradox we are diving into today.
Welcome to your custom-tailored deep dive.
It's a fascinating topic.
It really is. Our mission today is to explore this completely unexpected bidirectional feedback loop between artificial intelligence and the human brain. We are looking at a stack of cutting-edge neuro-AI research spanning from 2024 to 2026. Because for decades, the narrative was simple. Artificial neural networks were loosely inspired by biological brains.
We looked at neurons and we built software that mimicked them.
Exactly.
Okay.
But the script is completely flipped. We are now using the very AI we created to crack the physical and cognitive code of the human mind.
Okay, let's unpack this, because that is a massive shift.
It's a fundamental change in how we study ourselves.
Hmm.
We really have to look at the artificial intelligence we interact with on a daily basis, specifically large language models or LLMs like ChatGPT or Claude.
Which we all use all the time now.
Right. For a very long time, the engineering goal was purely imitation. The metric for success was simply making a machine sound indistinguishable from a human being.
Like a really advanced party trick.
Basically, yeah. But as these models scaled up to contain billions and then trillions of parameters, this strange emergent property appeared. They stopped being mere text generators.
What did they become?
They have essentially become an ultra-powerful microscope and a real-time simulator for human cognition. We aren't just teaching machines how to think anymore. The architecture of the machines is actually revealing to us what the biological process of thinking is under the hood.
That feels like a massive revelation. If our brains are operating like the software we just invented, it makes me wonder about the actual mechanics of it. When I'm sitting here talking to you, what is my brain actually doing that mirrors an AI?
Well, we finally have concrete data on that. It's thanks to some landmark studies out of the Hebrew University of Jerusalem and Google Research, published across 2025 and 2026.
Oh, wow. What did they do?
They wanted to see what happens in the physical brain during natural language processing. So they monitored subjects who were simply listening to natural, unscripted conversations.
Very much like the one you are listening to right now.
Exactly like this one. They specifically focused on Broca's area. That's the region of the frontal lobe heavily linked to speech production and language comprehension.
And I'm guessing they didn't just find, a vague similarity?
Not at all. The alignment is shockingly mathematical. Yeah. The researchers took the activation patterns in Broca's area and compared them to the internal processing layers of massive language models, specifically GPT-2 and Llama 2. They found a linear correlation. The way your brain processes the meaning of a sentence as it unfolds in real time maps directly onto the hidden layers of those AI models.
Wait, let me stop you there and push back a little, because that sounds almost too perfect.
Go for it.
Are we saying the biological, squishy human brain actually has a mechanical forward pass like a computer program running on a server? Or is this just a really convenient, trendy metaphor that scientists are leaning on because AI is the hot topic of the decade?
That is the crucial distinction to make. And for a long time, the neurobiology community assumed it was just a metaphor.
Because brains and computers are totally different materials.
Right. We thought, okay, computers process things linearly, brains process things holistically. But this new research suggests the parallel is a literal mechanical reality.
Really? How so?
Consider how an LLM generates a response. It does not conceive of a complete finished paragraph and then just print it out all at once.
Right, it goes word by word.
Exactly. It looks at the context, calculates the statistical probability of the very next token or word, generates it, and then runs the whole calculation again. It builds reality sequentially, layer by layer.
And the brain does that too?
Yes. The data from Hebrew University shows that the human brain does not wait for the end of a sentence to decode the meaning. It constructs comprehension in the exact same temporal, serial way, word by word, layer by layer.
So as I'm speaking this sentence right now, the listener's brain isn't just passively recording the audio, it is actively calculating the probability of the very next word I'm going to say.
Yes, essentially running a biological autocomplete in the background.
That is wild.
That is the mechanism at work. Both biological brains and artificial transformers are fundamentally optimized to predict the very next piece of context. And what makes this so significant is that it provides computational proof for a concept that neuroscientists have debated for years.
Which concept?
Carl Friston's free energy principle.
Ah, okay. I've seen Friston's name pop up in these sources, usually surrounded by incredibly dense math. Break down this free energy principle for those of us who haven't taken advanced statistics. What does it actually mean for my brain?
At its core, Friston's theory argues that the brain is essentially a prediction engine. Its primary goal in life is to minimize surprise.
Minimize surprise. Okay, give me an example.
So when you walk into your kitchen, your brain already has a predicted model of where the fridge is, what the hum of the appliance sounds like, what the floor feels like under your feet.
Right, I'm not relearning my kitchen every time I walk in.
Exactly. But if you walk in and suddenly there's a loud crash, there is a massive gap between what your brain predicted and the sensory data it just received.
And Friston calls that gap-free energy.
He calls it free energy. Your brain immediately scrambles to update its internal model to account for this new reality, thereby minimizing the free energy.
So it's constantly trying to bridge the gap between expectation and reality so it doesn't get totally overwhelmed?
Exactly that. It relies on Bayesian prediction machinery, meaning it constantly updates the probability of an event based on new incoming evidence.
Okay, I follow that.
For a long time, Friston's principle was a brilliant but highly theoretical framework. It was really hard to prove physically. But when we look at how a large language model trains itself...
Oh, by constantly adjusting its internal weights to reduce the error rate?
Yes. By reducing the error rate between its prediction and the actual training text, we realize we have accidentally built a working silicon model of Friston's principle. The LLM is a functional blueprint of the brain's biological drive to minimize surprise.
Here's where it gets really interesting. If our brains are fundamentally biological prediction engines and they use the same mathematical architecture as these AI models, it makes me wonder about the hardware.
Physical brain itself.
Yeah, scientists must have realized that if these AI pattern matching tools are so spectacularly good at decoding language, what would happen if we pointed that same predictive math at the physical anatomical structure of the brain itself?
And that logical leap is what completely rewrote the map of human neuroanatomy.
How drastically?
Well, to understand the scale of this breakthrough, we have to look at the baseline. For over a century, the absolute gold standard in neuroscience was the Brodmann map.
Right, Corbinian-Brodmann.
Back in 1909, Brodmann painstakingly studied brain tissue under a microscope, looking at how individual cells were organized, and he divided the human cerebral cortex into 52 distinct regions.
Wait, 1909. So for over 100 years, neurologists were basically navigating the most complex object in the known universe using a map that only had 52 territories on it.
It was an incredible achievement for its time, but yes, it was incredibly limited by human visual processing. A human researcher looking at a tissue sample can only see obvious structural boundaries.
Like where the cells get suddenly denser or where a major fold happens. It's like navigating the oceans with a hand-drawn pirate map. You generally know where the continents are, you know where the sea monsters might be, but the coastline details are incredibly blurry.
The pirate map analogy is incredibly apt. We knew the general coordinates of the motor cortex or the visual cortex, but the subtle subdivisions were just invisible to us.
Until recently.
Until 2025, when researchers at UCSF and the Allen Institute introduced a tool called the Cell Transformer.
Cell Transformer, so it's based on the same tech as ChatGPT.
They took the underlying transformer architecture, but instead of feeding it billions of words from the internet, they fed it massive, multidimensional data sets of brain tissue.
What kind of data?
We are talking about transcriptomics, the way specific genes are expressed in individual microscopic cells.
And because the AI isn't limited by human eyesight, it can look at all of that genetic data at once. What did it find?
It found boundaries we couldn't even conceive of. The Cell Transformer analyzed millions of subtle genetic and structural variations simultaneously.
Looking for patterns.
Looking for mathematical clusters of cellular behavior that represent distinct operational zones. And overnight, that 52-region map exploded.
Exploded to what?
The AI discovered over 1,300 previously hidden regions and subregions in the human brain.
Oh my God, from 52 regions to over 1,300. So we went from a hand-drawn pirate map to suddenly having a high-resolution Google Earth for the human mind.
That's exactly what it is.
You can zoom all the way down to the street view of our neural pathways. And I see in our sources that this isn't an isolated project either.
No, the momentum is widespread. We are seeing parallel breakthroughs like the Next Brain Atlas out of UCL in 2025 and the broader brain knowledge platform.
What do those do differently?
These initiatives are applying AI to standard, non-invasive MRI scans to visualize the adult brain in microscopic detail. The AI algorithms are finding patterns in the scan data that correlate with those newly discovered 1,300 regions.
The clinical application of this has to be staggering. It's one thing to have a prettier, more detailed map for a textbook, but what does this mean for someone sitting in a neurologist's office today?
It fundamentally changes the viability of treatment. AI is doing in a matter of minutes what used to take decades of manual postmortem dissection.
So diagnosing things earlier.
Earlier and more accurately. Take a condition like severe epilepsy. Often the seizures are triggered by tiny microscopic malformations in the brain tissue that standard scans and standard human analysis simply miss.
But the AI can spot them?
Yes. Or consider Alzheimer's disease, where the key to treatment is tracking the absolute earliest, most subtle signs of cellular degradation before massive cognitive loss occurs.
So with a 1,300 region map,
A neurosurgeon can target a laser ablation therapy, or a neurologist can monitor disease progression with a level of precision that was relegated to science fiction just 3 or 4 years ago.
okay, so we have machines that process language just like our temporal lobes do, and we've used the pattern recognition of those machines to draw a hyper-detailed 1,300 region Google Earth map of our physical hardware.
Right.
But humanity never stops at just drawing the map. Once we know where all the roads are, the immediate next step is trying to read the traffic on those roads.
We started pointing the AI at our actual real-time thoughts.
This is the part that blows my mind.
It takes us to the absolute frontier of brain-computer interfaces, or BCIs. Historically, the BTI field was quite rudimentary.
Like controlling a cursor on a screen.
Exactly. A paralyzed patient might wear an EEG cap, which measures electrical activity on the scalp, and after months of training, they could learn to move a cursor or select the letter on a keyboard. It was incredibly slow and frustrating.
But AI changed that.
The integration of modern AI models has changed the paradigm entirely.
The sources highlight a project called MindEye 2, which sounds like something straight out of a sci-fi thriller.
MindEye 2 is a perfect example of this leap. Researchers are taking fMRI or EEG data, which to the human eye essentially just looks like a chaotic bunch of squiggly lines.
Just a heat map of blood flow in the brain.
Right. They feed those squiggly lines into an AI, specifically diffusion models. These are similar to the AI engines that generate digital art from text prompts.
But here, the prompt isn't text.
The prompt is the brainwave. And the AI is able to reconstruct the physical image the person is looking at, or even just imagining visually on a screen.
But wait, my inner monologue, or the images in my head, they aren't clean, high-definition photographs.
No, they aren't.
And my internal voice isn't always speaking in complete, grammatically perfect sentences. It's usually a jumbled mess of half-thoughts, random anxieties, fragmented images. How on earth does an AI decode that kind of chaos into something coherent?
It is a brilliant technical achievement because the AI is not trying to read the abstract semantic concept floating in your subconscious.
And what is it reading?
Between 2024 and 2025, studies funded by the NIH Brain Initiative, alongside researchers at UC Berkeley, achieved breakthroughs by focusing on the motor cortex.
The part that controls movement.
Yes. When a paralyzed patient attempts to speak, even if their vocal cords or facial muscles cannot move, their brain still formulates the exact neurological instructions required to articulate those words.
It cues up the tongue, the lips, the breath.
Precisely.
So the AI is intercepting the physical blueprint of the word right before the body fails to execute it.
The AI decodes that specific motor formulation, what we call inner speech, and the results are astonishing. They achieve decoding accuracy rates between 79% and 97%.
That's incredibly high.
And because it is reading the motor intent, it isn't just spitting out a robotic monotone text readout. It captures the intended intonation.
Wait, really?
Yeah. The AI knows if the patient's internal formulation was a whisper, a shout, or a question, and it synthesizes the audio to match that intended emotion.
And our sources show this is evolving incredibly fast. By By late 2025 and 2026, the research expanded into what they are calling mind captioning.
Mind captioning is fascinating.
This is where the AI outputs highly detailed, continuous text descriptions of what a person is merely imagining in their mind's eye without them even trying to formulate speech.
They are even beginning to predict preconscious thoughts.
Preconscious thoughts.
The data your brain is queuing up milliseconds before you are fully aware you are even thinking it.
I mean, the implications for patients locked in by ALS or those who have suffered severe brainstem strokes are nothing short of miraculous. It completely restores their agency and their ability to interface with their loved ones.
It does. However, the dual-use nature of this technology presents a profound societal challenge.
Yeah, I want the listener to really put themselves in this scenario for a moment. Imagine someone narrating your inner monologue while you're standing in line at the grocery store right now.
It's an uncomfortable thought.
Every snap judgment you make about the person taking too long at the register, every random anxiety about a work email, that weird song lyric you can't get out of your head just scrolling on a digital screen for anyone to read.
It's a valid fear.
Where do we even begin to draw the line here? How do we balance an absolute medical miracle for an ALS patient with what could practically become the most terrifying breach of cognitive privacy in human history?
It is the most critical, practical, and legal debate of our current era. The technology to extract this data is advancing exponentially faster than our legislative frameworks can handle.
We don't have laws for this.
We have to answer fundamental questions about data ownership. When your raw, unedited thoughts are translated into digital packets and leave the physical confinement of your skull, who owns that data?
Is it protected health information?
Can it be subpoenaed in a court of law? Can the company that manufactures the BCI headset monetize your neural responses to an advertisement? We are moving into an age where cognitive privacy is no longer guaranteed by biology.
And while society wrestles with the practicalities of machines reading our minds, there is a completely different, almost paradoxical side to this neuro-AI loop that we need to look at.
The cognitive impact of relying on it.
Right. We've built software that mirrors our brains. We've used that software to map our brains, and we are using it to read our inner speech. But what happens to our biology when we start casually outsourcing our actual thinking to these tools?
This is where we see the biological reality of neuroplasticity clash heavily with the sheer convenience of our AI tools.
Our sources point to a major set of studies out of MIT in 2025. They wanted to look closely at what happens to humans who heavily rely on generative AI, like ChatGPT, for their daily cognitive tasks.
Writing emails, brainstorming, analyzing reports.
Exactly. And the physical evidence they uncovered is actually really concerning. It turns out that excessive reliance on these tools isn't just making us a bit lazy.
It is actively atrophying human cognition.
How did they prove that?
The methodology of the MIT study is what makes it so compelling. They didn't just ask people how they felt about using AI on a subjective survey. They hooked the participants up to EEG monitors to observe their brainwaves.
Okay, so actual biological data.
Yes, and the data showed that heavy, chronic AI users exhibited significantly reduced overall brain activity when they were subsequently asked to perform cognitive tasks independently, without the AI.
Wow.
More specifically, the researchers observed a marked decrease in neural connectivity within the alpha and theta frequency bands.
Break that down for us, because we hear terms like alpha waves thrown around in meditation apps all the time. Why do the alpha and theta bands actually matter for our daily intelligence?
They are critical for higher-order human thought. Alpha waves, which operate roughly between 8 and 12 hertz, are essential for a state of relaxed focus.
Like being in the zone.
Right. They are the waves that bridge the gap between your conscious and subconscious mind, allowing for creative problem-solving and lateral thinking.
And theta waves?
Theta waves, which are slower, around 4 to 8 hertz, are deeply involved in memory consolidation, the active process of learning, and navigating complex environments.
So what happens when we use AI too much?
When you rely on an external tool to do the synthesis for you, the brain stops generating robust connectivity in these specific bands. You are essentially dampening your biological ability to hold on to new, complex information and to generate original insights.
It feels exactly like taking an electric bike to the gym to do leg day.
That's a great way to put it.
Sure, you're moving incredibly fast, you're breezing up the steep hills, and you're getting a massive amount of miles done on paper.
Being very productive.
But underneath all that forward momentum, your actual leg muscles are doing zero mechanical work. The motor's doing everything. And as a result, your biological muscles are just quietly getting weaker.
The e-bike analogy captures the mechanism perfectly. Biological systems operate strictly on a use it or lose it principle.
Synaptic pruning.
Exactly. Synaptic pruning means the brain will dismantle neural scaffolding that it doesn't need in order to save energy. The practical fallout of this pruning is what researchers have termed the accumulation of cognitive debt.
Cognitive debt. I don't love the reality of it, but the term itself is incredibly accurate for what's happening.
The MIT study observed this debt in real time. When blind reviewers evaluated the output of users who relied purely on AI to draft essays or reports, the writing was consistently described as structurally sound but soulless.
Soulless writing. That makes sense.
But the more alarming finding was the impact on the users themselves. They had significantly worse memory retention of the very content they had supposedly just created.
Because they weren't fully engaged.
If questioned, they couldn't defend their arguments, connect the concepts to other ideas, or recall the nuances of the topics.
Because they didn't actually do the cognitive heavy lifting. The AI did the statistical forward pass, not their biological neural network.
Exactly. And this brings us to the ultimate tragic irony of this entire feedback loop. Humanity spent decades pouring billions of dollars into building a tool that perfectly mimics the predictive nature of the human brain.
And now that we finally have it in our hands,
That very tool is actively training the physical human brain to become less capable. We are externalizing the biological effort required to think.
and looking at the sheer mechanics of it makes you appreciate the raw biological perfection of the human brain even more.
Oh, absolutely.
I mean, think about the infrastructure required for AI. An AI server farm training a large language model requires massive industrial cooling towers, advanced silicon chips, megawatts of electricity. It literally has the carbon footprint of a small town just to generate text.
The contrast is staggering. The human brain achieves its miraculous processing power, managing language, sensory input, emotional regulation, and abstract thought, running on roughly 20 watts of power.
That is less energy than a standard refrigerator light bulb.
And beyond the sheer metabolic efficiency, the biological brain is highly plastic and deeply embodied.
Meaning what, exactly?
Meaning our cognition isn't just math floating in a void. It is intrinsically linked to our physical senses, our hormones, and our movement through physical space. AI, for all its immense predictive capability, is entirely disembodied, cannot replicate the whole-sick nature of human thought.
So what does this all mean? We've covered some massive, mind-bending ground today.
We really have.
We started with the realization that AI language models and our biological brains construct reality in shockingly similar ways, constantly predicting the next moment to minimize surprise.
Using Friston's free energy principle.
Right. And we've seen how AI has acted as an unprecedented microscope, blowing up our map of the brain from 52 crude regions to over 1,300 highly detailed territories.
Unlocking incredible precision for treating neurological diseases like Alzheimer's and epilepsy.
We also explored the very real frontier of brain-computer interfaces. AI is successfully decoding the motor formulation of inner speech and rendering mental imagery with near-perfect accuracy.
Which brings the promise of medical miracles for paralyzed patients, alongside immediate, pressing questions about data ownership and cognitive privacy.
And finally, we looked at the double-edged sword of this entire ecosystem, the looming crisis of cognitive debt.
Right.
Using generative AI as a daily crutch physically reduces our alpha and theta wave connectivity. It literally dulls the very creativity, memory, and focus we are trying to enhance with the technology. It's a profound balancing act.
It demands a conscious shift in our behavior. We have to ensure we are using AI to augment our thinking and handle the busy work, rather than allowing it to replace the necessary biological friction of complex thought entirely.
AI is unequivocally our greatest tool for understanding human potential, but if we aren't highly intentional about how we use it, we will just outsource our own mental sharpness to a server farm.
Exactly.
Which leaves us with a totally wild, forward-looking question for you to ponder long after you finish listening to this deep dive.
I'm curious to hear it.
We know our biological brains are these hyper-efficient 20-watt miracles. But we also know they rely entirely on physical, cognitive effort to maintain those vital neural connections. The brain prunes what it doesn't use.
That's neuroplasticity, yeah.
So if we continue to seamlessly merge with AI through these advanced brain-computer interfaces, if we start automatically offloading all of our complex problem-solving and memory storage to the cloud just to avoid cognitive friction, will future human brains physically shrink? If the AI is doing all the heavy lifting, generation after generation, could we eventually evolve into simple biological routers? Just fleshy antennas whose only evolutionary job is to pass raw sensory data up to the cloud rather than generating any original independent thoughts ourselves.
It is a chilling but entirely scientifically grounded possibility based on the laws of neuroplasticity. It forces us to ask what the core definition of human consciousness will be in an age of total machine symbiosis.
Think about that the next time you watch your robot vacuum bumping into the walls of your living room. The machinery we build outside of us is fundamentally changing the machinery inside of us. Stay curious, protect your cognitive leg day, and we will catch you on the next deep dive.